Show of hands, how many people here have taken Physics 1 before? Okay, so a little less than half the room has taken Physics 1. You'll be able to keep up with this. The rest of you will force yourself to keep up with this. Okay. So we're talking about polarity. And there's a big difference between bond polarity and molecular polarity. And molecular polarity is measured in terms of this symbol, mu, which stands for, which is the symbol for dipole moment. And the actual formula for dipole moment is Q multiplied by D, where Q is the charge and D is the distance. So basically, the easiest way I could say this in a sentence is that dipole moment is a charge separation, because it's a difference of charge over some difference of distance. We're not going to use this to calculate any numbers. The units for dipole moment are D. The units for this are capital D for debye. You could look up what that is. But we're going to use this as an idea here. Charge is in coulombs. This would be in meters. But to get that to work out, you need to use a conversion of coulombs, like stanocoulombs. Don't worry about that. The distance here is the important feature, the important aspect, because it gives this a direction. So in physics, there are two kinds of quantities. There are scalars and there are vectors. And scalars are those things that might have some kind of magnitude, some amount, and units, of course. But vectors, direction matters, and scalars, direction doesn't matter. Like if I said something has a mass of 50 grams, I don't need to tell you which direction inside it has a mass of 50 grams. But if I said I walked 25 feet, and then I turned and walked 15 more feet, how far did I get from my original starting point? Wouldn't you have to know how much I turned? Because if I walk 25 feet and turn 180 and then walk 15 feet, I'm only 10 feet away from where I started. If I walk 25 feet, turn 360, and walk another 10 feet, right? I'm 35 feet from where I started. So their direction absolutely matters. And this equation for dipole moment shows there's a distance in there, and it has a directional idea in there. So before we actually show how to use these vectors and do some vector addition, let's look at a couple of bonds. Carbon to fluorine, carbon to chlorine, carbon to bromine, and carbon to iodine. Which of these is most polar? You would probably guess the first one, right? It's got the biggest difference of electronegativity. And it does have the biggest difference of electronegativity. You know, carbon is a 2.5, fluorine is a 4.0, chlorine is a 3.0, this is a 2.8. Textbooks call this a 2.5. I'm going to write 2.5, cross it out, and write 2.6. I'll show you in a second why. So there's 2.5, there's 2.5, there's 2.5. By our definition of bond polarity, this should not be polar, and this should not be polar. This should be the minimum that's polar, because a bond is said to be polar if the difference of electronegativity of the two atoms involved is greater than or equal to 0.5. What'd I just say? If the electronegativity difference is greater than or equal to 0.5, then this is known as polar, a polar bond. If the electronegativity difference is less than 0.5, it's actually just known as not a polar bond. Is there any polarity to it? Sure, but we have a cutoff. That cutoff is actually based on this, carbon to hydrogen covalent bond. That's the actual cutoff. Just think, like dissolves like, right? You're all in the room with me here. Like dissolves like. Good. Water is definitely polar, you know that for a fact. And if you take, let's say, propane, which is this thing that has carbons and hydrogens in it, there's no way that'll dissolve in water. If you take any kind of, these things are called alkanes. I'm imagining you all took Chem 2. At the end of Chem 2, you even learned how to name some of these. If you take octane, for example, it won't mix with water. It'll form two layers. So that means if water is polar and like dissolves like, then these alkanes are not polar at all. So because the alkanes are not polar at all, you know there's no difference of electronegativity here, but there is a difference of electronegativity over here. So what was that difference? Well, carbon is a 2.5 and a hydrogen is a 2.1. So this is where this rule came from. They're like, oh, I guess 0.4 difference is not polar enough to make the molecule somehow polar, so we need to be more than that. So to call something polar, it's got to be 0.5 or more, right? You understand the root of this thing? And then there's this rule that if it's greater than 2.0, then it's greater than 1.9, it's ionic. If the difference is big enough. It's not true. Boron to fluorine, the difference is 2.0 exactly. That's bigger than 1.9, and it's not ionic. So we definitely know that it's going to be ionic if it's a non-metal connected to a metal. And sometimes that difference is less than 1.9. Sometimes it's greater than 1.9. And almost always, if you have a non-metal connected to a non-metal, that's going to be covalent, even in the case of boron to fluorine, which is 2.0 of a difference. In the right solvent systems, a non-metal and a metal could be very covalent-like, which we're going to study Grignards and see how in ethers they have 52% covalent characteristics. So it's what I said about organic chemistry before, that you know in Gen Chem you memorize a couple of rules, and here we start expanding and taking a look at all the things that break the rules. So for us, we're going to basically say that dipole moment, even though it's charge times distance, and for charge we could just summarize that as an idea of electronegativity difference. Distance has to do with the distance between the two atoms in the bond. So here's a little problem. This is the biggest electronegativity difference, so that's like the most charge. The thing is that carbon's the same size in all of these, but fluorine is smaller than chlorine, is smaller than bromine, is smaller than iodine. So here the distance gets bigger, gets smaller, gets smaller, gets smaller. So on the one hand, the charge gets smaller as you work your way down this column, but the distance gets bigger. You see, they're fighting antagonistic effects. In almost all cases that we are going to need to use, we could just say dipole moment is kind of like electronegativity difference. I'm just bringing up this case right here because it's an exception to the rule. So it's a very good idea to know the exception. If you have a table of dipole moments, the carbon to fluorine is 1.4 debye. The carbon to chlorine is 1.5 debye. So by dipole moment, it's more polar. Why is that? Because while this is a bigger electronegativity difference, these atoms are smaller, these atoms are bigger, the distance is bigger over here. But this is an exception to memorize. Then it continues as expected. This is like 1.3 debye. This is like 1.2 debye. So you see it's like a little switch. Had you just said, okay, forget this dipole moment thing, I'm just going to say the most polar thing is the biggest electronegativity difference, then you would say it's first, second, third, fourth. You'd almost be right. It's second, first, third, fourth. When I was a student, I saw this, I memorized it, and I was like, great, I understand this now. The carbon to chlorine is bigger, so it's going to be more polar than carbon to fluorine. Then I get hit with a quiz that says rank these. It's basically the same exact thing, except instead of carbon to these atoms, it's boron to these atoms. Being a logical person, I thought to myself, they're just switching carbon to boron, and the pattern should be the same, because in all these cases, it's always the same electronegativity versus the halogen that's more, less, and less. So it must be that this is the most polar, then this, then this, then this. It wasn't. I got it wrong. This is first, second, third, fourth. This just goes with electronegativity difference. Do you see what I'm saying? So, like, I'm just saying, this is a perfect MCAT question because it's an exception to just the rule that you expect. Biggest difference of electronegativity goes hand in hand with the most polar. That's what dipole moment is trying to explain to you, right? So this is the biggest difference of electronegativity. So it is going to end up having the biggest dipole moment. So there's something extra peculiar about this little switch. It's not just the size thing. And you know why it's not just the size thing, if you think about this logically? The difference here in electronegativity, carbon to fluorine, is 2.5 to 4.0, that's 1.5 units, versus 2.5 to 3.0, that's a half a unit, right? So this is 3 times more charged. Is chlorine more than 3 times larger? It's not 3 times large, it's not even 2 times larger. So like there's something else going on with the orbitals and whatnot. So can we just remember this? Besides that, now we're getting into the actual vector nature of this. If you have a molecule that has one polar bond, one single polar bond, the molecule is going to be polar. But if you have a molecule with more than one polar bond, it might not be polar. It won't necessarily be polar. And later in organic chemistry, too, we're going to learn about some molecules that have no polar bonds and somehow are polar. But that has to do with delocalization of charge, resonance, aromaticity, and so on. What am I saying? Here's a molecule, HCN. Is it polar? So we're going to draw these arrows for bonds that are polar. Like, we don't count this. Don't count carbon to hydrogen. We just said that it's based on the Orgo definition, difference of electronegativity. Just don't ever count carbon hydrogen. But this is a polar bond. Nitrogen is more electronegative than carbon. You can write partial negative, partial positive, or you could just draw this arrow, right? So there's only one arrow. This thing is polar in this direction. Fine. How about water? Well, that has more than one arrow. How about carbon monoxide? Dioxide. That has more than one arrow. And if we do this wrong and we draw it in a like Lewis structure kind of a way, then we can't see a difference. Should draw it as symmetrical as I can. Oxygen's more electronegative than hydrogen. There's a polarity that goes that way. But on the other side, hydrogen is less electronegative than oxygen. There's a polarity that goes this way. And somehow this thing becomes polar. This is polar. You know water's polar. Oxygen's more electronegative than carbon. Oxygen's more electronegative than carbon. And yet this is nonpolar. So sometimes you have things that have 2 vectors that are polar, and sometimes you have things that are 2 vectors that are nonpolar. To be not confused, I made an error on the board intentionally. And the error is I shouldn't use these vector arrows for molecules that I drew the Lewis structure for. I have to draw these arrows on molecules that have a real shape. So if the shape of this molecule around this oxygen is tetrahedral, I can't draw it linear looking. I have to have it tetrahedral. And then I could draw those arrows in. I hope you know that something with 4 electron domains is tetrahedral, at least for electron domain geometry. And if there's any lone pairs in there, then you kind of don't see them. So it could be trigonal pyramidal, it could be bent, all of that stuff. If it's 3 domains, it's trigonoplanar. If it's 2 domains, it's linear. Also, something with 4 domains is sp3. Does that make sense? So sp3, the electron domain geometry is tetrahedral. sp2, the electron domain geometry would be trigonoplanar. This is just a review. We haven't done this vector addition yet. We need that in order to... So to figure this thing out, this one topic of is the molecule polar, I know you've seen this in textbooks, like it says CCl4 is nonpolar, and it shows this and this and this and that, and somehow you're supposed to see this and understand what's going on. Nobody should really have any idea what's going on here because 2 of these vectors are not allowed to be drawn, so let's deal with that. But in order to even do that, what tools do you need? You need to know how to take a molecule's formula and turn it into a Lewis structure. From the Lewis structure, draw its actual shape. And then once you have its shape, you have to figure out where the vectors are pointing, where the dipoles are pointing. Once you have that down, I think we all have all the pieces of the puzzle down. We just need to know how to do vector addition. That's the physics thing that I said. If you've taken physics, then you know this. And if you haven't taken physics, then you're going to have some trouble, possibly. Who knows? There's 2 ways to do this. There's a graphical method, and there's a mathematical method. I'll do both, actually. I'm going to show you how to do both, because several of you have said you've taken physics, and it's a summer course. Why not? Let's start with the graphical one, so everyone can be on board here. So a vector is something that has magnitude, some number, like 10, 20, whatever, units, like feet, pounds, some sort of unit, and direction, right? We can draw an arrow to denote that vector. When I draw an arrow for a vector, this is now physics. I'm not drawing this arrow yet, because that's an arrow for a dipole. I'm drawing just any arrow that denotes any vector. It could be any vector. It could be force, newtons, right? That could be a vector. It could be displacement, meters. That could be a vector. What's important about this is, what's a vector? It's got 2 parts. It's got magnitude and direction. How we denote magnitude is the length of this arrow. So if I have a bigger vector, I'm going to draw a longer arrow. If I have a shorter vector, smaller vector, I'm going to draw a shorter arrow. So if I wanted to say I'm driving 50 miles per hour, that arrow should be 5 times longer than an arrow that would be 10 miles per hour. Does that make sense? The length of the arrow describes how much of it. And then direction is absolutely important here. So if I'm pointing this vector this way, that's totally different than pointing a vector this way. What are you allowed to do with a vector? You could transpose it. Transposition. What you can do is move it anywhere on the board you want, as long as you don't change the identity of the vector. What would change this identity of this vector? If I make it longer or shorter, that would be a different magnitude. What would change the identity of this vector? If I turn it to some other angle, that would change its direction. So I could put this vector, if I call this vector vector A, I can draw vector A right here, as long as I am careful to draw it in the same magnitude and direction. I mean, I'm on the board here, so if I was on paper and had a compass and a ruler and a crystal ball, then I would have it correctly drawn, right? But you see what I'm saying? That should also be vector A. This should not be vector A, and that should not be vector A. Okay. When you have more than one vector, you can add vectors. And the easiest way to do this in a graphical method is the head-to-tail method. There are other methods, but I feel like for a student who hasn't had physics and tried all the other methods, this one is the easiest. So Let's say I have vector A, which represents some sort of a force. And let's say I have vector B, which represents another force applied to an object. Let's make sure we understand. I have a refrigerator right here, and I'm pushing with a force this way, and another person gets right where I'm standing and is also pushing with a force this way. Won't both of our forces add? If I'm pushing with a force this way, but my friend who's trying to destroy me is on the other side pushing with a force this way, right? They'll somehow subtract, cancel. He'll maybe stronger than me, he'll run over me. I'm stronger than him, I'm running over, right? So this is vector addition that we're doing. From a top view, looking down from the sky, you would figure out how much force I'm putting in. Here would be the refrigerator. You'd figure out how much force I'm putting in. He's on the other side. You'd figure out how much force he's putting in, and somehow these are either completely canceling. What if he's over here? What if he's on that side? Do you see we're kind of going to go into that corner with that? But how do you know? What's the overall force on that? So you could do this vector addition. If these arrows mean something, that means I am pushing this with half the strength that he's pushing it. Do you see this? And if we do this head-to-tail addition, and you could do it with as many vectors as you want. We're going to say, like, let's say there's only two. Let's say I'm pushing it north and he's pushing it northeast, right? Great. I could either take the head of A and attach it to the tail of B, or I could take the head of B and attach it to the tail of A. I'm going to get the same result as a vector, same resultant. So first I'm going to do the A plus B, and then I'm going to do the B plus A. I take A and I transpose it. I move it anywhere I like on my page, as long as I draw A the exact same way that you see A over there, right? Let's pretend that's identical. No change of direction, no change of length. I'm doing A plus B, so to the head of A, I'm going to attach the tail of B. I have to be sure that I'm moving it exactly. Hopefully I moved that exactly. Do you see this is A, this is B. Now that they're connected at the head of A and the tail of B, you ignore the head and tail there. You ignore that. Your result goes from the tailmost tail over to the head. So from here to here, right here is your result. This is your result. Ignore that pathway. This is your result. Your length of vector increased. It's bigger than any of those, right? You got some addition. And it's kind of up and to the right. I'm going to write R for result. That was A plus B. Now if I do B plus A, I should get no difference in result, because it doesn't matter how you attach them head to tail as long as you attach them head to tail. So let's see if that's true. I'm going to slide B over. I guess to me this looks about right. And then to the head of B, I'm going to attach the tail of A. I hope that's correct. That looks approximately right. Now I go to the last tail, that's this one. Starting from there, I'm going to draw an arrow to the head over here. This result should be identical to that result. If I go ahead and erase all of the other nonsense around it, is it true that that result is identical? I would say close enough, right? I think I've made my point, right? Do you see those are same results? It doesn't matter how many arrows you have. You could draw, let's say we have A, B, and C. I could do this in a variety of methods. I can attach A to B to C. I can attach the head of that to the tail of that, and then the head of that to the tail of the next, and then get an overall result. If I don't like that, and I don't want to do too many things at once, I could attach A to B and get a result, take the result and attach C somehow to that result, like either the head of the result to the tail of C, or the head of the C to the tail of the result. Do you see? Good. What is this result? So here's A. Sort of. Here's sort of A. I think that's right. I might as well attach C next for no reason at all. I decided to go with C. Right? And then here's B. One important fact here is it doesn't matter where this last head is pointing. It's irrelevant. You ignore that. Just figure out where in space that is. This is the tailmost tail. This is the headmost head. You're going to draw from tail to head, and since I'm going that way, that's the direction of that arrow. Because look, this is A, this is C, then it's B. The overall result is supposed to look like this. There's my result, right? What if I add, let's say A, then B, then C, right? If I add A, then B, then C, notice the result is like this. Here C is pointing down, his result is pointing that way. See, it doesn't matter which way C points, it's just where the location of the arrowhead is. And if I did it right, that should approximately be that. What the hell do we need this for? When you draw dipole vectors, they're either going to cancel out or they're going to add. We don't care how far they add, we just care if they add. If I put together dipole vectors, a molecule has, let's say, dipoles in it, and I draw all the arrows properly, and then I add them all up, and I get some result, that means the molecule's polar. And if it turns out that they all cancel out, how could you have something cancel out? What if you have two vectors, A, and then B is actually the same as negative A, right? Do you see how it would go 10 feet up and then 10 feet down and they cancel? So this would be a totally nonpolar result. So we could use vector addition to go over those two things. Here's water. Well, only in its liquid form. It's dihydrogen monoxide, H2O. Here's carbon dioxide. And you don't put the vectors in these. You have to draw their actual shapes around the central atom. What is the shape around that central atom? The electron domain geometry is tetrahedral. There's 1, 2, 3, 4 domains, right? So this thing is tetrahedral. We put an oxygen. We put these bonds. I think I've already described in this room what this is showing you. This is a tetrahedron. This is going in the plane of the board. This is in the plane of the board. This is coming out of the board. This is going into the board, right? Coming out, fading in. I have to put two lone pairs. The easiest thing to do, since the lone pairs are not the polar vectors or whatever. What are the polar vectors? The H to O or the H to O or the other way, O to H, whatever, bonds. The easiest thing to do is to put those bonds in the plane of the board. I actually shouldn't, if I'm trying to draw vectors, put those bonds over here. I've been saying what I'm about to say for years. Only a small handful of students get it, it seems. If I draw an H right here, then I could say, well, there's a difference of electronegativity and distance, and we're just going to summarize dipole moment as just a difference of electronegativity, because usually that's correct. When the CF to CCl, that there's a difference there by some reason. If I put the H over here, we know O is more electronegative than H. I can draw a vector going this way. Do you see this? But here's a problem. If I put the H over here, I can't draw a vector going this way. Let's see how many of you can catch on to this. A vector absolutely matters how long it is. That's its magnitude. And absolutely matters the exact perfect correct direction. The problem with this right now is that this wedge is representative of where the atom is. This wedge tells us that this hydrogen is coming out of the board. But how am I drawing the vector? I'm not drawing it out and into the board. I'm drawing it on the page. Do you understand? Like, let's say I had a BB gun and I'm standing over here pointing it at the O. It's very different than pointing it on the paper upward. You can't draw a vector on a board to represent in and out. Vector has to be the exact proper direction. For that reason, we're going to have problems anytime we have three-dimensional bonds going to atoms. How are we going to even deal with that? That's going to be part of the homework that I'm going to give you. To think through this, how are we going to deal with it? We could deal with, up until now, and I'll show you how to, we're going to easily be able to deal with anything that's in the plane of the paper. So let's say this way on our paper is the x-coordinate, up and down on our paper is the y-coordinate. Any vector in an xy system we're going to be able to deal with. It's just z going in and out of the page is going to be a big problem for us. Not just for us, for anybody. It's always been a problem. So look, to make this simple for us, I'm going to put hydrogen over here and hydrogen over here. I hope you all understand why I put it there. because now I could draw vectors. Since the bond's on the paper, I could draw the vector on the paper, because it indicates real direction here. You see what I'm saying? Of course, this is a lone pair, and there's a lone pair. It's a weird thing I just did. I made a bond to a lone pair. It's not a bond to a lone pair. It is a lone pair. So there's a lone pair going into the board. There's a lone pair coming out of the board, right? But now that I have the real shape of this, I can put dipoles in here, the dipole vectors in here, and when there's more than one dipole vector, when there's 2, 3, 4, 5, that's when we want to know if the molecule's polar or not. Oxygen's more electronegative than hydrogen. So I could draw a dipole vector like this, right? Isn't it true that oxygen's more electronegative than hydrogen? Here's the thing. Is this right? The way I drew it on the board. It isn't. It isn't. Do you know why? So for those of you that don't know why it's not right, is this right? I mean, if an OH is this magnitude, how can an OH be that magnitude, right? You have to have the magnitudes right. If you have different, like on some side of the molecule it's OH and somewhere else it's SH, fine, draw in different sizes. The lengths are going to be based on the difference of electronegativity. That's how we're going to deal with it. So the difference of electronegativity here and here are exactly the same. We should have the same lengths. So you would use something to help you. I don't know. I'm going to use this eraser. If this is one eraser length this way, this is going to be one eraser length this way. Do we see that? And now we use the vector physics that we've just done. A, B. Anyone taking physics this semester coming up with Orgo? Terrible idea. But we're doing chapter 3 right now. I'll tell you why it's a terrible idea. A lot of people think you need to get it all out of the way. I don't know. Pick something else in life and try to think of the same getting it out of the way. I want to be a fashion designer. So on the same day, I'm going to learn how to sew and hem and use leather goods. There's no way you're going to learn all that. You're going to be crappy in a lot of things rather than great at anything. Of course, there's certain kinds of exceptions, and we could discuss if you need to. Email me. Maybe I'll have time to make an appointment. But generally speaking, somebody who's not gone to a high school and taken AP Chem in physics and doesn't already know a lot of this, starting from scratch, you're just setting yourself up to not do great. But I love when students say, I'll take my chances. Roll the dice on your future. There's better lotteries to attempt, right? Attempting the lottery to get to medical school so you could work your ass off for many years is a bad choice of lottery. Mega Millions is a better choice of lottery. You know, like if you're going to play the lottery, might as well just play one that if you win, you don't have to work after it. But anyway. So here we have two vectors. And this is chapter 3 in a physics book, Vector Edition. What we are looking for here is not the overall result for water. Water has a dipole overall of 1.8 dBi. You don't need to know this at all. That's why I'm erasing it right away. Well, actually, not true. If I know it, you should know. But eventually, not right now, not today. What we want to do is just figure out, is this polar or not? So the point is, when we add the vectors, do they add? Is there a start and a finish? Or is start and finish the same point? Because if start and finish is the same point, there's no actual result. If I walk 10 feet, turn around, walk 10 feet, my start and finish is the same exact point. Nonpolar. So is this? I'm sure some of you could even see it already, that the polarity goes this way. Do you see that? But just add it head to tail. Just because this one you see doesn't mean you're going to see all of them. There's going to be ones that you don't see. So here's, how do you add a head to tail? You can add A. And to the head of A, I'm going to add the tail of B. Here's B. Do you see how the result ends up going? It starts here and it finishes here. Here is the result. There's the result. Here is the result. Do you see that result? Maybe my result is a little too powerful. Okay, that's a better result, right? Do you see that result? So this is polar because we got a result. We got an arrow going somewhere. How about CO2? Turns out this is the correct shape. Not only is this the Lewis structure, but it's the correct shape. How many domains are around that carbon? There is 2 domains. They're double bond domains. 2 domains is linear. Oxygen's more electronegative than carbon, so here is bond vector A. Oxygen is more electronegative than carbon. Here's vector B. This is tough to put together because if I draw it, it's going to be confusing. So you have to watch me draw it to understand how they're going to I mean, mathematically, negative 10 and positive 10 is 0, right? But if I draw it, how do I add A to B? So here's A. And to the head of A, so I have to put my marker right here. I put the tail of B, and then I draw B that ends over the, because it's, so there's no start or finish is the point. So it's nonpolar. It's totally nonpolar. BF3 is a compound that has some of the most polar bond. The bonds are so polar, boron to fluorine, that bond is so polar, books would say that difference of electronegativity is big enough to be ionic. To make kind of sense, look, let's say you have an atom A and another atom A. They're identical, same electronegativity. If they have a covalent bond, obviously they have the same pull on the electrons will be right in between. But if you have A and B might be more electronegative than A, then the electrons could be a little bit more towards B. That would give this a little partial positive, a little partial negative. What if B is even more electronegative than that, and the electrons are even closer, and it's like a real partial negative and a real partial positive? And what's the limit of this? If you keep going with this idea, eventually you get to the point where B has the electrons completely and is an anion, and A lost them and is a cation, do you see? And they decide the cutoff is 1.9 or greater, but we know that boron, fluorine is a covalent bond, so it's not ionic. But what's interesting is that compound is not polar. The whole thing is not polar, even with the most polar of bonds. So how do we do that? How do we work that out? Number one, we put boron with 3 fluorines. We get the Lewis structure going. Why do we care so much about any of this? Because it's going to be tested. But if you have like idealistic, why do we care about this? Because one day we're going to talk about amino acids. And have quite a distance between their charges, quite a big charge separation, quite a big dipole. And then when these amino acids are linked up in proteins, you have things like alpha helices and beta pleated sheets, and those alpha helices have long dipole vectors through them. So when you're studying that eventually, you're going to want to know what's going on, and not just give up and memorize last year's exam hoping it's the same questions. Okay, so here's BF3. How do we deal with it? Boron has 3 electrons plus 7 times 3, which is 21 electrons for the 3 fluorines. So that's 24 electrons in total minus 2, 4, 6. It equals 18 electrons to place. I place them on the outer. 2, 4, 6, 8, 10, 12, 14, 16, 18. I ran out of electrons. Do you notice now we're going to have like 3 resonance contributors because boron doesn't have its octet, so you could bring this in or bring that in or bring that in. But that's not going to change anything for what we're trying to do. Because if I just draw 1 resonance contributor, it might confuse us with trying to draw vectors for dipoles. But if you draw all 3 resonance contributors, you're going to see that the bond from here to here to here to here to here to here is all going to be the same, right? Do you realize if I bring this in, it'll be double bond or double bond or double bond? So the bond order here, here, and here will be the same. And the atom boron to fluorine has the same difference of electronegativity of boron, fluorine, boron, fluorine. So we don't have to draw those resonance contributors to figure out polarity here. What we just have to realize is once we're done distributing the electrons, how many domains are around that boron? The answer is 3. And even when we do resonance, there's still going to be 3 domains around the boron. So what is the shape around that boron? Trigonal planar, right? So if I draw boron with fluorines perfectly trigonal planar, that's about as great as I'm going to draw it on the board. Now I put in the vectors. Let's call this A. Well, if that's A, which is, let's make it 1 eraser size, then this should be B, which is the same size. And this should be C, which gives me the same size. And I could do this in one of two ways. I could add A to B to C, and if that confuses you, you could just add two of them, A and C, for example. See what the result is, take that result and add it to the other one, right? Let me do it in both kind of ways. I'm going to add A, B, C, and I'll do it simple. I'll just add the head of A to the tail of B and the head of B to the tail of C. So I transpose A. Here's my A. There's my A, right? And to A, I add the tail of B. So the head of A, tail of B. So I need to transpose that here. Here's B, right? And then I'm going to transpose C. Everyone seeing where C is? I'm going to transpose C. I'm going to put the tail of C to the head of B. What do you notice happened? There's no start, there's no finish. The result is they cancel each other out. Now I know that there are some textbooks or some schools that try to like simplify some things, just memorize this for an exam. So sometimes they say, even if you have polar bonds in molecules, if they're all the same bonds and the middle atom has no lone pairs, then it's nonpolar. Great, so that's one specific case. This works for all cases. This is what you do to know whether some molecule, and that thing that I just said only works when there's one central atom. What are you going to do when it's this? Or this? Or this? That's not a central atom with lone pair thing. This, all three of these, you're going to need to use these vectors to work this out. So adding A to B to C went full circle. It didn't get anywhere. It's like me walking 10 feet, turning around, walking 10 feet. If I add two of them, just two of them, A and C, look what happens. Here's A. And to that, I'm going to add C. To the head of A, I'm going to add the tail of C. Here's C. So what's the result from A to C? From here to here, here's the result, R. What do you notice about the result and the one I didn't put in, B? Do you see they're the same length, 180 degrees apart? If you've got same vectors, 180 apart, they're going to cancel out for sure. Now this is for those of you who want to get above a 508 on the MCAT eventually. Some of you are watching. If you want to get above a 508, you need to intermix these courses. You know, like you're not going to get to the MCAT and they're going to say, "Ready? Here's the Physics 2 question. This next question is Orgo 1." Right? It's all intertwined. Right? So I'm showing you that I'm intertwining physics. How do you add vectors in physics? Turns out you can only add mathematically. This we just did graphically. I hope you get it. I hope you figure out the graphical thing. Mathematically, you could only add vectors that are in the same direction. So how do you do that? Turns out you could break up a vector that's got direction into its components. What am I saying? If we draw an XY coordinate axis, those of you that are terrible at math, you have one of two choices. You can either stop listening right now for a little while, and then realize you've got a big problem coming up eventually when you get to the MCAT, or you could listen the best you can and try to figure this out. Let's say I gave you two vectors, and they were both on the positive x-axis. It's really easy. Let's say one vector, vector A, was +5 on the x, only on the x, and vector B was +7, only on the x. Well, they're both in the same direction. I could add that +5 and +7 is +12. No problem. What happens if vector A is +5 on the x and vector B is +7 on the y? You can't add that. Not like in a 5 + 7 kind of a way. You realize that if this is going this way, 5 units, and then the other one is going directly upward 7 units, then my result is from here to here, and we're using things like a squared plus b squared is equal to c squared. So you need two things to describe a vector, the result and also like an angle between it. And how do you get the angle? You should know that sine of theta, cosine of theta, and then there's tangent of theta. Sine of theta is equal to what? Opposite. Now, opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. Here comes high school math. Tangent of theta is opposite over adjacent. So do you see that I have for this angle, I have an opposite and an adjacent, so I could figure out what its actual angle is? Because it's just going to be 7 over 5, and then it'll be inverse tangent. And then I could figure out what this length is right now. By what? By 5 squared plus 7 squared and square root that whole thing. Do you see? Well, it works in both directions. If I gave you a vector that's on the x and a vector that's on the y, and you could add them, you get an overall vector. But I could describe this overall vector by using its pieces, its components. So if I gave you a vector with an angle, you could break it into its x and y. Why you would want to do that is, imagine I gave you two vectors. One has this length and that angle, and the other one has, let's say, this length and that angle, whatever these angles are. And I ask you to add them, not graphically, because graphically you just slide this over here and say the result is that way. Mathematically, I want numbers here, which you can't add this to this. That's like adding x and y. It doesn't work, right? What you could do is say, I'm going to take this vector and break it up into this triangle to get its y piece and its x piece. I'm going to take this vector and break it up into this triangle to get its y piece and its x piece. Do you see that? And add the x's and add the y's and give me an overall mathematical result. Do you see how that works? Let's do one example, the BF3 problem. Since we just did BF3, let's do this for BF3. So we had 12 people watching. Now we have 9 after this lesson. They feel like this is not important. It's a shame, because I run across too many people who feel like it's not important. Then there are people that work hard and learn what I teach them. Then they take the MCAT. And the people that work hard and learn that what I teach them, they get 518s, 520s. They go to the best medical schools in the world. And then there's people that try to take all the prep courses and do all these things, and they get 502 and 504 and can't understand why. And it's real simple. You need to know all this stuff. This isn't for an exam. Here's an eye-opener, possibly. You get to medical school, and what do? You open up your first textbook, and it's chemistry and biology and physics. Who knew that? Who knew that you needed to learn this because this is med school? Some of us don't understand this. Why do you need physics? Because there's a course called respiratory physics, where you use physics too, Kirchhoff's laws, to describe how blood flows. The same junction rules that you have in wires, you use those things to describe how blood flows. Because, you know, you've got an aorta, then you have capillaries, right? So you use these rules. For some reason, people think they get to med school and they're going to do what they love. They're going to get a scalpel and they're going to start cutting, right? That's not how it goes. This is medicine. This is the atoms that work. You're going to then figure out how they combine to make things like enzymes. And then an enzyme might have a deficiency or might be overactive. For example, there's a particular virus that activates this enzyme that destroys a tumor suppressor gene, so tumors start springing up, right? How does that work? How do you cure that? With a scalpel? Maybe, maybe not. Maybe you'd have to know this to know the limitations of your medicine and so on. So, see how many more people no, all 9 are still here. Good. Paying attention. All right. So we're doing the BF3 problem. For that, we need a Cartesian coordinate axis. Thank you, Descartes. Okay. So in the middle, there's going to be the boron, right? And to make life easy for myself, I'm going to put a fluorine atom over here. So this sphere represents boron, this one represents fluorine, this way represent fluorine, and this way represent fluorine. So what do I have? I've got one vector. Look, I hope you're realizing we're doing this. B, F, F, F. Here's the vectors. One this way, one that way, one that way. I didn't have to draw it this way. I could have drawn this vector on the x-axis. Do you see? I could have drawn none of the vectors on the x or the y, but if I draw one of them on the y or the x, at least I don't have to break that one up into components. So that helps. This vector is completely in the positive y. I don't need to break it up into anything, because I'm going to be able to add it to any other y's. This one is not in the x or the y. It's got some amount in the x and some amount in the y. I'm going to have to break that up into its components. This is also not in the x or in the y. It's some amount in the x and some amount in the y, so I'm going to have to break it up into its components. Because all of these three are the same power, I'm just going to call this a 1, a unit of 1. That would be its magnitude. Look, what is the actual dipole? Let's say the boron to fluorine bond has a dipole of 1.3. That'll be 1.3, and that'll be 1.3, and that'll be 1.3. So I just divide all three of them by 1.3, and it's 1 to 1 to 1, right? So that's, I'm allowed to draw 1 here as long as I also draw 1 as a, if that was an F and that was a Cl, I can't draw 1. I would need to use its actual values for those bond dipole moments, right? Okay. This is a 1. And now the question is, how do I break that up into its components? I need to break that up into the pieces of this triangle, right? I need to know this angle theta. How do I find that angle theta? Well, do you realize this is trigonal planar? What is the angle here? What's the angle here? What's the angle here? The angle from F to B to F, any F to B to F, is 120 degrees. So this whole thing is 120. And do you notice the y to x makes a 90-degree angle? So this whole thing is 120, and that's 90. Isn't this 30? Because 120 minus 90 gives me a 30. So I have a triangle. This is what you're looking at. I'm trying to break this up into components. I have a triangle with 30 degrees over here. And the hypotenuse is 1. And I'm trying to find what this side is. And compared to that angle, this is the adjacent side. And I'm trying to find out what this side is, and compared to that angle, that is the opposite side, right? So I'm looking for adjacent, and I have angle and I have hypotenuse. Angle, adjacent, hypotenuse. Cosine of 30 degrees is equal to adjacent over hypotenuse. And if I'm looking for adjacent, I could just move the hypotenuse over there. So hypotenuse times the cosine of 30, that's my adjacent distance. That's the leg. Do you see this? Now, since 1 is the value of my hypotenuse, it's just the cosine of 30 is that adjacent portion, right? So this is equal to the cosine of 30. What about the opposite? Not the opposite of what I just did. I mean, the opposite line, leg, right? So there's the angle, there's the opposite, there's a hypotenuse. Opposite hypotenuse. Oh, someone's forgetting it. So sine of 30 is equal to opposite over 1. And I move the 1 over there, and it's only 1 because I'm turning all of them into unit vectors, right? Great. So opposite, this is going to equal to the sine of 30. We also have to realize the following. Which way are things pointing? So do you see, to go to here, you're in the positive x, but negative y, right? You're all witnessing this? We're almost done with this. We're almost done with this. But those of you that took physics, you really should use your physics to apply to here and review what you're doing. Those of you that didn't take physics, you're going to really, really love the fact that I helped you with this before you take physics. Who's taking physics again? Nice refresher. Do you remember this at all? I hope you do. If you don't, this is the simplest part of physics. This is the reason why people mess up physics. because they don't learn this in the beginning, and then everything else is just scrambling when they could have just learned this, when they could have learned most of Physics 1 is like vector addition. So here is what this becomes. Look at what we're doing here. I still have this unit vector over here of 1, but instead of having this line going this way, I broke it down into a line going this way and a line going that way. Do you see that? Do you see how I turned it into those components of the triangle? Like, the point is, I could walk diagonally across a block or get to that same place if I walk up one block and turn right and walk the... What was this piece? This piece, remember this piece of the triangle? This piece was the cosine of 30, and this piece was the sine of 30. But this piece is actually the cosine of 30, while this piece is the negative sine of 30. Why negative? Because it's pointing down, right? Negative sine of 30. Are you at all paying attention? If you are, then you'd realize this is identical to that in like all ways. From here to here, you build a triangle. This is 30 degrees for the same exact reason. So if this is the cosine of 30, then we got something going this way, which is the negative cosine of 30. And then, of course, this leg going down that way, that's the negative sine of 30. Right? Now what I can do is add up all of my x's and draw a new graph and see how far on the x it went. Separately, I add up all of my y's, and on the new graph, draw how far on the y it went, and that will be my result. It's the same exact thing as taking these and adding them head to tail. What should my result be, by the way? 0, it's BF3. We just did this, right? But let's double check. For the x, it's cosine of 30 plus the negative cosine of 30, which is 0. Cosine of 30 plus negative cosine of 30 is 0. So it's 0 on the x. What about on the y? It's 1 plus the negative sine of 30 plus the negative sine of 30. How many of you here know what the negative sine of 30 is worth? Yeah, so a couple of us are answering, and I'm not sure if you're answering because you remembered negative sine of 30 is 0.5, or you're just being logical here, and since it's canceling out, 2 of these equal to a 1, so each of them is a half. Does that make sense? We're following? And it is. Sine of 30 is 0.5, so negative a half and negative a half plus 1 is completely canceling out, right? One major question I've had for many years is, I don't mean for myself, I mean for my students. I've answered it, and some students were able to answer it, not right away. Some students took weeks to answer this. The CF4 problem. It's a really simple problem. Prove that CF4 dipole moment equals 0, which means it's nonpolar. Here is how some students tried to prove it. See, they're all canceling out. Why is this wrong? Somebody in this room, sorry online, I can't ask you to tell me. Why is this wrong? Somebody in this room tell me what's wrong with this. Yeah, so they said it's the Lewis structure, and absolutely, this is not a plus sign. This is not flat with 90-degree angles. I can't use fake angles for my vectors. They need very real angles, right? Like I went to the carnival, and I used the BB gun to try to win the big bear, and I had the wrong angle. Well, I'm not going to win the bear, right? I didn't shoot out the hole, right? So this couldn't be more wrong. And, you know, what else is wrong is doing what the textbook shows. The textbooks like to show whatever it wants. That doesn't mean that's how you do physics vector addition. When the textbook shows this as its actual shape, what's wrong with this? Anyone following? Yeah, I can't draw vectors going out of the board or into the board. Now I can. Now I can. Used to be I couldn't, but now if I go on Amazon and I buy one of those 3D pens that could draw in the air with plastic, you know what I'm saying? Then I could draw a vector. I still will have a problem going into the board. I'd have to drill into the board, right? So you got to find a better way to do this. I would like you to do this, prove, and you could do one of two ways. Graphically, or how we just broke it up at sine, cosine, tangent mathematically. I think as a preliminary, you should stay away from the mathematical aspect of it. Try to do this graphically. There was a hint on how to do this. There was a hint in the lesson. Unfortunately, I'm going to erase it from YouTube within about 4 hours, so I'll give you till midnight. You could rewatch it. Somewhere in the lesson, there was a hint on what to do. It wasn't an explicit hint, but if you paid attention to how I said the various ways, I'm giving too much of a hint, the various ways you could add vectors, then perhaps you could get creative here and figure out what to do. So solve this. It is solvable. The solution might depress you or upset you, not upset you when you look at it and you're like, that's it? Yeah, that's it. It's not necessarily the toughest problems or the most complicated, convoluted things. Sometimes it's just, you got to look at it slightly differently. How do you deal with those? How do you deal with those? Here's one summary. When we have two vectors, if the two vectors are 180 degrees apart, imagine the black marker cap here is the arrowhead, right? So these are arrowheads. If the two vectors are 180 degrees apart in the same strength, they're going to cancel out completely. If they're in the same direction, then they'll add completely, right? So the point is, the bigger the angle between them, the more they cancel. The smaller the angle between them, the more they add, right? Here you've got three compounds. They are alkenes. And these three alkenes, let me draw them a little better. There are your three alkenes. Dichloro, we'll learn how to name eventually. Maybe, yeah, probably not before this summer session ends. But this is a 1,1 dichloro ethene. This is a 1,2 dichloro. It's trans, and this is a 1,2 dichloro. That's cis. That shouldn't be extremely foreign. Some of you have just taken Chem 2, and you kind of maybe know this. The thing is, though, are they polar? Are any of them polar? Here's a question. Here's how Orgel convolutes things. On an exam, you could see these three. Right now, you have to be in the right mind frame to get what I'm about to say. You came to an exam. That doesn't mean you just did a lesson on dipoles and vectors. So you have no idea that the question could even be about dipoles and vectors. It could be about resonance. It could be about a bunch of things. You see these three molecules, it writes A, B, and C, and the question says, which one of these is most soluble in water? And like, because this is the topic of the day right now, and we spent a lot of time on it, maybe you would figure out what I'm trying to say. But you get to an exam, you're like, soluble in water, you start panicking, because that's how strong you need to know these things. So you think soluble in water, which is like water, water is polar, which is more polar? Ah, dipoles, vectors. Add them up, right? Which of these is most soluble in water? Which one is least soluble? Which is most polar? Which is least polar, right? Carbon to carbon's not a vector in terms of polarity. Carbon to hydrogen's not a vector in terms of polarity, but carbon to Cl is. By the way, how do you make these problems a little better for yourself? Like, we're at level 1, by the way. Like, I hope you're not thinking like, wow, we did so much more. There's plenty of schools in the country that are going substantially deeper than this. And you're competing for a seat in downstate medical school, for example, not with the peers in this room or watching online. You're competing with people globally. Everybody wants to go to medical school and get a seat, right? And there's really Notice so far all of the problems that I've done had a couple of vectors, but they were the same length. Like the BF3 problem, it's BF, BF, BF. It wasn't BF, BCl, BH. You know what I mean? Like, so that would be like the next level. What about different atom, like change one of these CLs to a BR, now you have to draw different lengths. And almost always, you're going to draw the longest one as the most electronegative difference, right? Except that one exception. which is C to CL, is longer than C to F, strangely enough. So here's your vectors there and here. So it's kind of, I think, for anyone paying attention, it's kind of easy to follow which one is least polar. Because it's this idea that these two vectors, there's vectors that are 180 degrees apart, they're going to cancel out the most. And the ones that have an angle between them, now we should really see, if there's two vectors, they're 180 and they're the same size, cancel completely. And if there's any angle between them, they add to some amount. The less of an angle between them, the more they add, right? So this cancels out completely. This dipole moment is 0. What about this and this? Are they equally polar? Somebody's very good at geometry, then perhaps geometry, trigonometry, you're going to be able to differentiate between these. Other people are going to say, so this is trigonal planar, the angles here are 120, so it's like 120, or these are 120, and these are all 120, everything's 120, it's not 120. Where is there a wider angle? Let's take a vote. Somebody said the angle there is wider, but who thinks this has a wider angle? Who thinks this has a wider angle? Okay, so for those of you at home, are you raising your hand? For this one, I had 0 votes as the wider angle, and for this one, I had 0 votes for the wider angle. Let's try again. Let's give it about 5 seconds. I seem to gain a follower now. Somebody joined in. Okay, hold on. I'm not asking about the because. Now we have a lot of talking in the room. Hold on. Who chooses this as the wider angle? Who chooses this as the wider angle? So we got 1 and 1. Let's now work it out. The angle between these is 120 degrees, about, plus or minus a little bit, right? A little less than, a little more than. But the point is that carbon is trigonal planar, right? These are single bond domains. That's a double bond domain. These squeeze a little, so maybe this angle's a little less than 120, 119, 118, 117. What about this? This is more of like it's not an angle between two, it's an angle between 4. So what's the angle between the vectors? So we needed some sort of a reference frame. You see, this vector is some amount away from a vertical vector. If I draw a vertical vector, my question is, what's this angle? So I'm going to draw a straight line like this, right? From here to here is around 120. You're aware? And this portion, of course, is 90 degrees. So what is this angle? You see that's 30? Does that make sense? Again, this whole piece is 120. And if I draw a vertical line right here, then this portion of the 120 is 90 degrees. So from here to here is another 30. So what's the angle between these two arrows? The answer is 60. Because away from the vertical, this is 30 and this is 30. That makes them 60 apart. So do you see these are vectors A and B that are 120 degrees apart, while these are vectors A and B that are 60 degrees apart, and the smaller angle between them add more? If this was on an exam and you did vector addition, it would work out for you simply because they would print the molecule and the molecule would have all correct angles. But when I draw them, I'm drawing it as trigonal planar as I can, but it's not perfect when I'm drawing it. So if you put in the arrows, it might actually look like this is wider apart than that. Do you see what I'm saying? This is where using the math kind of helps. And we should use that. Polar or nonpolar?
Polar.
So it would look like it's nonpolar, and it turns out that this picture is deceiving, and it's a Lewis structure, and it's not the actual correct picture of it. And the real correct picture of this looks like this. But you wouldn't be able to figure that out just by looking at that picture. You would need to use the actual bonding orbitals to figure out why this is so. So we have to get started on that. We have like 6 minutes to just introduce that, and we're going to continue on this in our next lesson and at least finish up chapter 1 properly. How do I draw this in its proper orbital picture, like showing how everything is bonded? I'm not talking about like energy levels. I'm talking about, and you've seen these pictures in the book, they have like bubbles for bonds and these bubbles for pi bonds and so on. This carbon has what hybridization? So how many domains does it have? 1, 2, 3, 4. It's sp3, right? And it is connected to another carbon that's sp3. They're both tetrahedral. We need to see something about a carbon atom. A carbon atom that's sp3, we're going to draw like this. It's my best attempt at drawing that, but using its orbitals. So one thing, whether it's an sp2 orbital, an sp orbital, an sp3 orbital, we're going to draw it like that. It's going to look like half a p orbital. Okay? So do you see what I'm trying to draw is sp3 orbital up, and sp3 orbital down to the right, and sp3 orbital out of the board, and sp3 orbital in the back, right? That's what a carbon that's going to look like when it's sp3. A carbon that's sp2, this is very important before I continue on that, is going to look like this. It's going to have 3 orbitals that are going to be sp2 trigonal planar to one another. So I could draw them in the plane of the board. You see, I drew them in the plane of the board. Or I could decide to draw them in the plane of the floor. I basically took this right now, picked it up, and turned it like this. So one orbital goes that way, and then 2 orbitals go this way, right? Great. This is sp2. Let's remember that if it's sp3, it's using sp, p, and p. If it's sp2, it's using spp, and then it has a p orbital left out of it, right? Where is that p orbital? So that p orbital can't be mixing. When you mix s and p orbitals, they combine. If this p orbital somehow didn't combine, it can't be anywhere near those other orbitals. The word is orthogonal. It has to be orthogonal to all orbitals. For us, we could basically say that's 90 degrees. Orthogonal really kind of means away from everything. Some of you will understand that in this picture, some of you will understand that in this picture. It doesn't matter. If you have an orbital up, then the p orbital, this is an sp2 orbital, there's an sp2 orbital, there's an sp2 orbital. This sp2 orbital is pointing on the, let's say, y-axis. That means that free p orbital can't have anything to do with the y-axis. This and this orbital are pointing along the x and the y. Do you see that? So again, this free p orbital can't have anything to do with the x or the y. So where's that p orbital? It's in the z. It's going in and out of the board. Best I could draw it is like that, right? Like, I'm not trying to draw diagonally. It's in and out of the board. I just can't draw in the air. And since it's a p orbital, I'm going to shade one side of it. I like to shade the front. It kind of makes it look 3D a little more, but whatever you want to do, it's your picture. How would it look like over here? How would it look like over here? So this is the same thing, just turned sideways, right? You got an orbital on the x. Here the 2 orbitals are in the x and the z, let's say. So where is that p orbital? Not on the x, not on the z. It's going to be on the y only. And you're going to shade one side of it, right? Do you see this? You know what this looks like? The sp3, those orbitals look like a tetrahedron. But when you have sp2, take the 3 sp2 orbitals and the p orbital that cuts through them, and it looks like a trigonal bipyramidal. Doesn't it look like those 5 lobes of a trigonal bipyramidal? Extend that one deeper. What does an sp look like? What does an sp look like? So you can have carbon with 2 orbitals that are sp and sp, right? Since it's sp, doesn't it have a p orbital that has not hybridized and another p orbital that has not hybridized? Look, if I'm taking this as my Cartesian coordinate axis, x, y, and z, right? Then it must be, where we're assuming it must be, the px that's part of this hybrid system, right? So what's left? The py and the pz. You see those have not joined forces and hybridized? So an sp3 has 4 orbitals around it that look like a tetrahedron. An sp2 has 3 orbitals plus a p orbital, and count all the lobes, it looks like trigonal bipyramidal. And an sp has 2 orbitals and then 2 unhybridized p orbitals, but if you add up all the lobes, doesn't it look like an octahedron? Right? We're going to use all of these shapes to build molecules and to see their sizes and figure out why that molecule that I drew last, this one, called a dichloroalene, doesn't have the shape that it looks like. Like if one side is up and down, the other side is in and out of the board. So we start with, we're going to go over by like 3-4 minutes today. Maybe 5-10 minutes. No, 3-4 minutes. How do we draw this? So you start with the fact that you have a carbon, and this carbon is tetrahedral, sp3. So I'm going to draw its sp3 orbitals. I could draw one up this way, one that way, one out of the board, and one into the board, right? Everyone sees that, I hope. Now, one of its sp3 orbitals are connected to a hydrogen. Another sp3 orbital is connected to a hydrogen. Another sp3 orbital is connected to a hydrogen, right? When you don't practice this enough, you're going to draw a hydrogen in there. That doesn't make any sense. What's a bond? And a bond is a constructive interference between an orbital and another orbital. So carbon's sp3 orbital mixed with hydrogen's, what kind of orbital? S orbital. What's hydrogen's orbital look like? A sphere. It's just a sphere. So I'm going to draw past this sp3 orbital, somewhere out here, a hydrogen with a sphere around it, and where the sphere overlaps the sp3 orbital, that's the bond. So you recognize that. So I should draw another hydrogen out here, another hydrogen out here. Have you seen pictures like this? I'm sure you've seen this in the book. And then that carbon is going to be connected to another carbon. What do I draw? Carbon over here? No. That carbon's sp3 orbital is covalently connected to that carbon's sp3 orbital. So way further out, somewhere over here, I draw a carbon that has an sp3 orbital. Do you see the sp3 to sp3 link? What else does it have? It's got 3 more sp3 orbitals. I just have to draw it in a way that they're tetrahedral, right? You see, if one goes up, one goes to the side, 2 other go in and out. This one's up to the side, so I could draw one down, one out, and one in. Do you see I kind of inverted what this picture looks like? Do you see this tetrahedral thing is just this upside down? So if I put a hydrogen over here, a hydrogen over here, a hydrogen over here, and I could describe this. This is a carbon sp3 to hydrogen s sigma bond. Isn't that true? That right there, it's carbon's sp3, hydrogen's s sigma bond. Hydrogen is going to be the only one that's going to be inside some kind of a circle, because it all has is the s orbital. Everything else is going to have like a teardrop coming off of it. What is this? This is a carbon sp3 to carbon sp3 sigma bond. Because I don't want to go greatly over, I'm going to just show one more, and then we'll start with we will start from here in the next lesson. How do I draw this? I'm about to show you something. I'm about to prove something based on what we've learned before. You know, this is trigonal planar, right? And this is trigonal planar. But why do they have to be in the same plane? Why can't they be in perpendicular planes? Like, who's to say they're both trigonal planar or on the same plane? Well, we're about to see. This carbon is trigonal planar. I could draw it in the plane of the board, in the plane of the floor, whichever way I want to draw it. I'm going to choose to draw it in the plane of the floor. So here's a bond, an sp2 orbital going that way. Here's one going into the board. This one is out of the board. This one's into the board, and this one's in the plane of the board. Do we see this? And that carbon is connected to this carbon through its sp2 orbital linked as well. Now here's the thing, if this carbon has 2 more sp2 orbitals, why do I have to draw them out of the board and into the board? Why can't I draw them up and down? This is really important, that hopefully you're focused on this so you could start the next lesson the right way. Let's say I drew this one right, I mean it's trigonal planar. I put a hydrogen over here, I put a hydrogen over here. So let me put on the board what I mean. So far I drew this. That part's true. Very trigonal planar for that first carbon. I know we know that it's flat planar, but that's because of what reason? We memorized this, somebody told us. What about, can we determine it? Can we determine? On one case, let's say, what about this going up and down? Look, this is trigonal planar, that's trigonal planar, so this is trigonal planar, this is just a different direction trigonal planar. Is this true or false? Let me put a hydrogen over here, let me put a hydrogen over here. How about this? I'm going to make them in the same plane. This goes in front, this goes in back. Here's a hydrogen, right? What's left? What did I not draw over here? There's supposed to be a p orbital. It's supposed to be a p. We don't know about a pi bond yet. We know there's a p orbital, right? People are saying there's a pi bond, but what we know is there should be a p orbital. If I drew this right, where is that p orbital? So if this goes out of the board and into the right, you can't have it anywhere in this space. It's going to have to go up and down. So the p orbital will be like this, and I'll shade one side, right? Something like that. Forget that for a second. Just forget that for a second. And just look at this side. You have to ignore that side. Where is this p orbital? Where is this p orbital? If there's something in the board, out of the board, on the side, then it can't be in, out, or on the side. What it has to be is therefore up and down. How about this? I'm not even going to finish shading this. How about this? If this is in and out and whatever, then it has to be up and down. But if this is up and down, then this p orbital has to be in and out. Well, which one of these is a pi bond? Is this a pi bond? Or is a parallel overlap a pi bond? So do you see why it can't be this and has to be this? Because when these orbitals are in and out, both in the same plane, the p orbitals end up giving us a pi bond. Do you see the pi bond? Are you aware of the pi bond? So see if I taught you enough, I think I did, for you to work this out, try to practice this on your own. See if you could figure out why this alene should not be drawn this way, the way that I'm drawing, but should actually be drawn this way. Meaning if one side is up and down, then the other side has to be in and out for the hydrogen atoms. And the only suggestion I have is do what we're doing here, but start building it from one side and ask yourself, is there a necessity for these orbitals to go up and down or in or out or whatever? And then it's fine if you get stuck. It's fine if I didn't cover this enough for you to perfectly understand it, but we'll pick up from it. We'll pick up from here next time. Thanks for your participation.